In this video, I want to look at tangents and normals as an application of differentiation. So we know from our work in Year 10 and Year 11 that the tangent and the normal to a particular curve at a point are perpendicular to each other. So we've got one line that's green, the other line that is yellow, and they are at 90 degrees to each other. And if you take the gradient of the two lines and multiply them together, you get -1. And the relationship between the two gradients themselves is 1 is the negative reciprocal, which means 1 over. So -1 over the reciprocal of the other. The other thing that we know about tangents and normals is that they are both straight lines, and so they'll have an equation of the form y equals mx plus c. And the c is the y-intercept for the tangent line, so over here. And the m is the gradient or the slope of the line. We also know for a straight line that the angle that that straight line makes with the positive direction of the x-axis, so from coming from this direction, is tan of theta. And that's theta is the angle there. So we know that the instantaneous rate of change for a particular function, the instantaneous rate of change at a function at a particular point, so say this point here, is the gradient of the tangent to the curve at that particular point. So the gradient of this line. And this line is the tangent line, so it'll have a straight line formula, and it'll be in the form of y equals mx plus c. But we also know that the instantaneous rate of change is also the derivative of that particular function evaluated at that point. And so what we have here is that the gradient of the tangent at the point A is in fact f dashed of A, which means the equation of the line y equals mx plus c will in fact be y equals f dashed of A x plus c. We also know for tangents as well, or for vertical lines more specifically, that if you have a vertical line, the gradient is undefined. And so if the tangent that you're looking at is a vertical line, because the gradient is undefined, then the derivative is undefined. And the equation of a vertical line is x is equal to something. So let's have a look at y equals x to the power of a third. At x is equal to 0, we have an infinite gradient here at x is equal to 0. And so because the gradient of the tangent is the derivative, and the derivative is in fact the limit of the slope of the function as x approaches a, then we know at this point here that coming in this way the slope is getting steeper and steeper and steeper. Coming in this way the slope is getting steeper and steeper and steeper, and so what we end up with as a limit is a vertical line. And that's true at a cusp as well. If you think about the derivative as being the slope of this line, so what's the slope of the line at this point? What's the slope of the line here? What's the slope of the line here? And you can see that as we're coming this way, the slope is becoming steeper and steeper and steeper from the left-hand side. From the right-hand side, if we do the same thing and we're thinking about the derivative, the slope of the line is becoming steeper and steeper and steeper. So what we've actually got here is a vertical tangent at this point, the steepest that it can get. And the equation of that tangent is in fact x is equal to whatever that a value is there. And that works whether your cusp is pointing down or whether your cusp is pointing up. Okay, so the key to it is to remember that the derivative is the limit of the slope of the function, the limit of the slope. That will help you to determine whether the function is defined or not. So one of the things we're often asked to do is to find the equation of the tangent or the normal. So to find the equation of the tangent or the normal is to find the equation for a straight line. So to find the equation for a straight line, you need 2 points, or you need the gradient and 1 point. So we've got 2 points here, x1, y1 and x2, y2. So point 1, x and y value, point 2, x and y value. And so to find the gradient, you do y2 minus y1, x2 minus x1. And that will give you the gradient of the line. And you can substitute that into your equation for the line. The other thing that you can do is to substitute in one of those points to find the value of c in y equals mx plus c once you know what the gradient is. So your gradient can go in here. Your gradient can also go in there. So to find the equation of the tangent at x is equal to a, we need to know a couple of things. We need to know the gradient of the line, which will be f dashed at a, and then we've got to find some value for the y-intercept of that tangent c. So what we've got here, here's our function. The x value is equal to a at this point, and so the coordinates of this point are a and f of a. So we're going to use this point, a and f of a, to find this value of c, which is, when you draw the tangent back, the y-intercept for the tangent. And so if we know that the gradient is f dashed of a, then our equation y minus y1 equals m becomes y minus y1 equals f dashed of x, x minus x1. And we can replace y1 and x1 with this point here, that we know the x value is a, so we put an a in here, and the y value is f of a, so we put f of a in here as well. And so if we know what the function is, and we know what the value of the point is, we can substitute that value of the point into the function itself to find this value, the derivative of the function, substituting the a, and then put the a value itself in here. And when we simplify this, we'll have the equation of the tangent. And the equation of the normal is exactly the same process, but instead of f dashed of a, we have the negative reciprocal of f dash of a for the gradient of the normal. This is the gradient of the normal, and that will replace our gradient value there. So let's do an example. For the curve with equation y equals x squared minus 4x plus 5, let's find the equation of the tangent to the curve at x is equal to 3, the tangent, and then we'll find the equation of the normal at x is equal to 3. Now, make sure when you finally come to give your answer that you have an equation. Both of these questions ask for the equation, so it's not just enough to give the left-hand side. You have to have something like y equals, or y with a subscript t is equal to. Okay, so to find the equation of the tangent, we need to know two things. We need to know the gradient at that point, and we need to know the coordinates of one point on the curve. So our gradient is going to be f dashed of x, and the coordinates of the point on the curve are going to be our a value and our f of a. So let's find this for a. Now you'll notice that the equation is y is equal to, so when we're finding the derivative we should use dy, dx, etc. Now it is okay to use f dashed of x and f of x if you define the function y as being equal to f of x. Then you're okay to go. Right? So in the exam you need to make sure that you're using the form of the equation that you're given, unless you define it as f of x or y, whichever is comfortable for you, and then at the end you have to give it in the correct form. So in this question here, at the end, the equation of the tangent is going to be in the form of y is equal to. So if I do this, let me define, we just say let y equal to f of x. And so now we're looking for f of a, f of 3, which is 3 squared minus 4 times 3 plus 5, which simplifies down to 2, which means that the point x is equal to 3, y is equal to 2 is on the curve and will be our a, f of a. So now let's find the gradient of the curve. So f dash of x is 2x minus 4, and when we evaluate that at our a value, which is 3, we get. So now let's find the equation of the tangent. So the formula for the straight line, y minus y1 equals mx minus x1, becomes y minus 2, because y1 is our 2, equals 2, because that's the gradient, x minus 3, because that's our x1 there. If we tidy this up by expanding the brackets and then adding 2 to both sides, not subtracting 2, adding 2 to both sides, we end up with y is equal to 2x plus 4, and this is our equation of the tangent. And so to do part B becomes much simpler because we can actually work from this level here, or even this level here, replacing this gradient here for the tangent with the gradient for the normal, because we're evaluating at the same point, x is equal to 3. So let's just go ahead and do that. So you get y minus 2 equals negative 1 over our original answer before, 2, x minus 3. If you expand out these brackets, you get minus a half x plus 3 on 2. Add 2 to both sides, and now we've got y is equal to, tidy this up again, and with a little bit of careful fraction addition, you'll end up with the equation of your tangent being y is equal to negative a half x plus 7 on 2. And finally, I want to look at some of the more difficult sort of questions that have been asked involving the tangent to the curve. And they are the ones where you need to find a particular parameter, either as an a value for an unknown x value at the point at which the tangent occurs, or sometimes even within the equation themselves they might have a parameter that you need to find, and we'll look at one of those in a sec. So this question says the tangent to the curve with equation y equals e to the 3x, so an exponential, at some point on the curve a e to the 3a, so some point on the curve where x is equal to a, that tangent passes through the origin, and they want us to find the value of a. So we know the tangent is going to have a gradient that is equal to the derivative of this particular function, and it'll be evaluated for this particular x-axis. So our tangent of our function is going to be y of the tangent is 3e to the 3x plus c, whatever that happens to be, and then we're going to evaluate that at the point a and e to the 3a, and what you get is that if the y value, if the y value is e to the 3a, so we put this value in here, and we put the a value in for our x, this is the equation that we get. And you can see here we've still got the plus c from the equation. So what I'm going to do for this solution, I'm going to get the equation of the tangent, the whole equation, to, instead of be in terms of x, be in terms of a, so that I can solve it to find this a. So let's see how we go about that. So we have e to the 3a equals 3e to the 3a times A plus C. Let's solve this to get C, and when we do, that's the value that we get for C. And so what we're going to do next is we are going to put that back into our equation, and now we have an equation for the tangent that we can use. So we've got a gradient in there. We can also use this point here as our x1, y1, and we can substitute those values in here. And what we'll have left is an equation, when we do that, an equation that just has A's in it that we can solve for A. And so when you substitute in 0 for the y and 0 for the x's, so a 0 here and 0's here, what we're left with is 0 is equal to this equation here. Now you can already see there's a common factor here that you could take out. But before we go and do that, let's just be a little bit cautious, because there's actually a couple of ways that you could go about solving this. Let me just pull this out of the way over here. Okay, so let's have a look at the two solution processes that I've got here. Pull it all the way in. Good. Okay, so what I've done on this side here is I have done what I had just mentioned and factorised out the e to the 3a, and that leaves me with e to the 3a multiplied by this bracket here is equal to 0. So here we can use the null factor law, that says if AB is equal to 0, then either A is equal to 0 and or B is equal to 0. So either e to the 3a is 0 or 1 minus 3a is equal to 0. But e to the 3a is in fact, here's your e to the 3a, that's the graph of e to the 3a, and you can see that the y values for that are always positive. So e to the 3a is always greater than 0. So when we come back up here, this value is always greater than 0, which means that it must be this value here that is equal to 0. And if that's the one that's equal to 0, then 1 minus 3a is equal to 0 and a third is equal to a. The other way that you can do this is in fact you've got two terms here, both of which contain e to the 3a. If I move that up out the way, it now says e to the 3a. And what I'm going to do is I'm going to make each term one on either side of the equal sign, and then I can either divide both sides by e to the 3a, because that's always positive. But another way to think about it, let's divide e to the 3a, because that's never 0, e to the 3a. The other thing that you can think about it is in fact that what you have in front of this term here is a 1, and so 3a must be equal to 1, which is what we've got here. Either way you end up with this, and then you get that a is equal to a third. So the solution process for this one was that I went through and I found the tangent equation in terms of a, the whole tangent equation. But there is another way that you can work through these sorts of problems, and I'll show you in the next question. So this question says, for a particular value of m, the tangent to the curve f of x equals e to the minus mx plus 3x. So the m is a parameter in our equation here. At x equals minus 6, that tangent passes through the origin. They want us to find the value of m for that particular case that makes the tangent line pass through the origin. And this is actually a VCAR question from 2012 in exam 1. So this has to be done by hand, no CAS. So we know that the function is e to the minus mx plus 3x. So we're going to need to know what's the coordinates of the point that this tangent is touching the curve on. So we're going to substitute in, we know that we're working with x is equal to minus 6, and so we substitute minus 6 into our function for f to find our coordinates of our point. So when we do this, we end up with the equation e to the 6m minus 18, and what that means is that our point on the curve that also passes through the line, this is our a value that we're evaluating it at, and this is our f of a. Or if you like, this is x1, y1, our point for that. But the other interesting thing that we can do here is that we know that the point that the tangent line goes through this particular point here. We also know from in the question that the tangent line passes through the origin. Now I've just got the slope going this way. I have no idea which way the slope goes, but somewhere else along that line somewhere is the point 0, 0. Now, given that I've got 2 points on the line, I can in fact, using rise over run, find the gradient of that tangent line. And I know that the gradient of the tangent line is equal to the derivative of that function evaluated at x is equal to a. So let's go ahead and evaluate f of x. And remember, be really, really careful with your derivative of your exponential. Minus m comes out the front. And for 3x, the derivative is just 3. When we evaluate that at x is equal to minus 6, x is equal to minus 6, substituting in minus 6 for our x value here, that becomes a positive 6m. And then what we're going to do is we're going to make this equation here equal to our gradient at the top. So let's do that. So this is our, I've actually done it the other way. This is our derivative at minus 6 being equal to the gradient of that particular tangent at that point. And then what I've got now is an equation that I can solve to find m. So I'm going to go through and do a little bit of manipulation to find m. So multiply both sides by minus 6, expand the bracket, collect all my terms onto one side and simplify. And again, I've got 2 options for a solution here. One where I can take a factor, the other one where I can equate the 2. If I take a factor, again, I get this null factor law thing here. 2 things multiplying to give you 0, 0. Either the first thing is equal to 0 or the second thing is equal to 0. So what we can have here, and I didn't do this before, I should go back and do it. We know that this is an exponential graph that looks like this. So what I should have done in the previous question is go and mark that as not equal to 0. I've got a statement underneath that says that e to the 6m is greater than 0 for all of m. So that kind of covers me. Best to go back and put that. And so our solution to this equation is that m is 1/6. So if we go back up to the top of the question, if we go all the way back up to the question, the particular value of m, that the tangent for that curve at x equals minus 6 passes through the origin is 1/6.